Alright, just going to go through the next video in this series where we're going to look at different types of errors. So hopefully in this wee section we'll do three things. Firstly, we'll describe what a random error is and how we can reduce them. Number two, describe what a systematic error is and how they can be avoided. And then finally, we'll look at the key differences between accuracy and precision. So first of all, just to get a pictorial overview, you can see that errors can be broken into two different branches. Number one, random errors. Number two, systematic errors. And of course, these errors can lead to uncertainty. So you might just want to pause the screen now and copy down the information. Now, firstly, random errors. So a random error is a chance difference between the measured value of a quantity and the true value of something. And these errors have got no pattern. And these random errors are unpredictable and they can't be replicated by repeating the experiment again. Now, examples of random errors include human error, such as limitations due to sight and touch, maybe natural changes in the environment, which would lead to changes in these control variables. Maybe think about wind and maybe temperature change. And of course, those things during an experiment could impact the results. And finally, something that maybe you haven't come across in GCSE, and that is a parallax error, which we'll look at a little bit later on. And that's if a student was to randomly place their eye either above or below the ruler when they're taking measurements. The key word there being randomly. And again, you might just want to pause the screen and copy down these respective notes. Now, ways in which we can reduce those random errors. Number one, we can use the average value or the mean value for a set of measurements during investigation. And number two, we can increase the sample size, so by taking more readings. So again, if you just want to copy down those bit of notes now for a few seconds. And that really ticks off the first learning objective, where we now know what a random error is and also how random errors can be reduced. The second type of error we'll look at here now is called a systematic error, and it's a consistent or proportional difference between the measured and the true value of something. And a systematic error is usually caused by measuring instruments that are incorrectly calibrated, as we'll see now shortly, or used incorrectly, which we'll see now shortly as well. So we're going to look at a couple of different examples of systematic errors, but before we do so, again, you might want to pause the screen and copy down these respective notes. The first type of systematic error we'll come across here now is referred to as a zero error. And again, sometimes there can be a zero error in the instrument, such as a ruler, as we'll see in this illustration below. So you can see this lower ruler here. The end of it has been carved off, maybe just with a lot of usage and whatnot, or perhaps maybe it's been used in a technology and design department or something, and it's maybe been struck by some sort of equipment that's ended up trimming off one end. Now this error will basically, if you're using this lower ruler, that zero error will throw off all your readings by that particular amount. And if you look closely, it seems like this lower ruler has got a zero error of approximately 3 millimeters. And so all readings you take using this ruler will in fact be 3 millimeters bigger than they really should be. So again, if you just want to pause the screen, take down the notes, or perhaps just a wee quick sketch of the ruler at the bottom with the zero error built in there. Now, we could of course also get a zero error on the needle of perhaps one of the older ammeters and voltmeters. So perhaps whenever you disconnect the circuit, the little needle does not go back down to zero. So in this case, you can see it seems to have a zero error of about 0.1 or so. So every reading would be approximately 0.1 bigger than it should be. And again, that gives it that systematic error for all the set of results. And again, if you want to copy these notes down on the diagram as well. Now, a zero error could really be built into a huge number of instruments. One that happened a couple of years ago for a CCEA paper was using a Newton meter, and it had a zero error of 0.5 newtons incorporated into it. And so basically, whenever there was no load applied, the screw at the top was adjusted such that whenever there was no load, the meter was reading 0.5 newtons. So again, this is coming from one of the previous CCEA AS level questions. You got this sort of zero error built in. And then the student was really expected to measure the weight of something and then basically subtract the 0.5 from it to get that true value. And again, as every single reading would be 0.5 newtons higher than the true value, this again would be an example of a systematic error. And again, if you just want to copy down those notes, perhaps a wee quick sketch of the diagram too. Another example of a systematic error is called a parallax error, and this wee diagram showcases very clearly it's all to do with reading lengths, distances with a meter rule or any sort of meter, or like a 30 cm ruler, 15 cm ruler, or a half meter rule as well. Now, if a student consistently reads from either too high a location or too low a location, again the key word is consistent, they're always going one way or the other. They're always coming up from too high or they're always coming from too low. This will either end up giving them consistently too high of a reading or too low of a reading for all their sets of results. And of course, whether it's too high or too low will depend upon the location of the eye, either top side or low side, and also the orientation of the ruler. That basically means, do you put the 0 of the ruler on the table or down low, or do you put the 0 at the top on the higher value, 100 centimeters at the bottom? So that'll determine whether or not your readings are too high or too low in each case. So every reading would therefore have this built-in error carried throughout every single result, and so again it would be a systematic error. So again, if you just want to pause, copy down the notes, and definitely copy down that diagram as well. Now, the two ways in which you can avoid a parallax error that you really need to make sure you do for A level, you could avoid it by quite simply reading the ruler at eye level. So you can see this central diagram. If you get your eye level down to the same height as the point that you're looking to measure, perhaps the bottom end of the spring, again that helps to avoid that parallax error. Similarly, in some experiments, if you can't get the ruler tight across towards the instrument you're looking to measure, you can use a set square, and of course that square can be leveled up and one edge can be parallel to the edge of the ruler, which means of course the top end coming off is going to be perpendicular to, and of course it can be traced away across to the object and take it back to the ruler to give you a much more accurate reading. So again, if you want to copy those notes down and the diagrams as well. Now, in summary, to reduce systematic errors across the board, we should conduct the experiment with care. Make sure you check to make sure there's no zero errors or whatnot, and make sure again to avoid those parallax errors. You could also repeat the experiment with different equipment to try and minimize the impact of those systematic errors. Now, regardless of how many times you repeat the experiment, that will not reduce or not eliminate those systematic errors. So repeats do not help in relation to reducing those systematic errors. And again, if you just want to write down that wee title, Reducing Systematic Errors, and copy down the respective notes as well. And that really ticks off the requirements for learning objective 2. You hopefully now know what a systematic error is. We've been through quite a few examples of them, and also really how they can be avoided as well. To finish up, we'll now look at the difference between accuracy and precision. So accuracy is how close the measured value is to the real value. Precision, on the other hand, is how close the measured values are together. And so you might have several measurements, and they can be described as being precise if the values are very, very similar to each other. And look, the wee diagram below I think illustrates very clearly the differences between accuracy and precision. You can see the first set of results are accurate. All the dots, maybe imagine that to be maybe even darts that are, or maybe perhaps even like arrows coming from a bow and arrow. They're accurate because they're all quite close to the center point, the bullseye basically. They're also precise because all the arrows, all the readings, the measurements are very, very close together. Now the next ones are accurate. You can see they're not that far away from the actual bullseye, but they're not precise. They're not all very, very tight together. They're spread out quite a bit. The next set of results you can see are precise. They're all very close together, but they're not accurate. They're very far away from the bullseye. And you can see the last set of results are neither precise, they're very spread out, and they're not accurate. They're all very, very far away from the actual central point as well. You definitely probably want to copy down these notes and definitely copy down the diagrams as well to deepen your understanding of the key differences. Finally, the type of error that you have will have an impact on whether the results are accurate or precise. So if we've got no errors, for instance, hopefully if the experiment is done properly, they're accurate, they're all close to the center point of true value, and they're also quite precise. They're all very tightly bundled together. If you've got a random error in there, the results can still be accurate. They're still quite close towards the center location, but those random errors mean they're not precise. They're not all tightly bundled together. If you've got a systematic error built in there, your parallax error, or of course your zero error, look, the results may not be accurate, as you can see in this diagram, but they are precise. All those results are very, very tightly compacted together. And if you again just want to pause the screen, copy down the notes, and certainly those diagrams as well. And finally, a series of results that have a random error, as you can see in the very center here. They can be a bit out from the true value either way, lower or higher. But of course, by taking a large series of results and then getting the average, the overall average can be accurate, even though the results, as you can see here, may not be precise. A systematic error, when it's involved, the results may be precise, as you can see here, very tight together, but they're not accurate. And again, just to stress that you will not reduce that systematic error by taking a large number of results and averaging. It doesn't help. And if you just want to pause and copy down just those lower two paragraphs to supplement your diagram. And that really finishes up learning objective 3, where you can now describe the difference between accuracy and precision. And that really finishes the final part of this 4th recording.